Know how to calculate LUP factorization of a matrix. How does this help us solve systems? Well, quite similar to LU factorization. Okay, what we have is when we perform a row swap on our coefficient matrix, we must also perform the row swaps on the right-hand side vector. So essentially Gaussian elimination. So whenever you swapped your coefficient, you also swap your right-hand side. So P was applied to A as well as P being applied to B. Well, we've factorized our matrix A so that PA equals LU. Okay, so therefore, instead of PA x, I've got LUX equals PB. If I let Y equal UX, and I substitute that in to this expression, so instead of UX, I have Y, I can solve this equation here for Y. So this is my lower triangular L times some vector Y equals P, which I've calculated, times B. Once I've got Y, I calculate X by solving UX equals Y. Okay, so we're going to have a look at that now. Right, so I have this 3x3 system. This is the same one as used in a previous example where we calculated the LUP factorization. So this is my L, U, and P. So what we do is this is L and this is Y. So we're going to solve LY equals PB. So there's my L and that's my P. Easy way to see this one is, okay, if you go across the rows, the top row has a 1 in the second column. So in other words, that means, so 1 in the second column, so that means the 4 is going to move up to there. This has got a 1 in the third column, which means the 8 is going to move up to there. And this is a 1 in the first column, which means the 6 is going to go down to there. Okay, so if we apply the row swaps to our right-hand side vector, we have this system solved by forward substitution, and we get our Y vector. That's not the solution. That's like halfway to the solution. Once you have your Y vector, you can then solve UX equals Y by back substitution, because U is an upper triangular. Okay, so once you have your Y, stick it on the right-hand side. There's your U. Solve by back substitution, and you get the solution. That's using partial pivoting. Now, these matrices, which are all used in the examples, they're nice round whole numbers. They're quite small numbers. That's deliberate because I didn't want the calculations to be that difficult. But when you have ill-conditioned systems, when not using partial pivoting may cause inaccuracies. So LUP factorization is preferred because it's more accurate, because it takes into account partial pivoting. Okay, there's a worked example on page 102, which we're going to go through now. Okay, and this uses or makes use of the LUP factorization we just calculated. Okay, so if you notice, this coefficient matrix is the one which we just did at the start of the lecture. So if we want to solve this system and we know LUP, the first thing we do is solve LY equals PB. Okay, so my lower triangular matrix was 1 0 0 0 1 0 1/3 2/3 1, and Y1, Y2, and Y3 are our unknowns. Our P matrix was 0 0 1 1 0 0 0 1 0, and that's multiplied by the right hand side vector. Okay, so we've got to solve that. If I multiply the right-hand side out, well, you can multiply it out, but you'll see there's a 1 in the third element of the first row, so therefore that's going to be 18. There's a 1 in the first column of the second row, so that's going to be -4. Therefore, that should be 6. Okay, so that's hopefully that's quite easy to see where I got the 18 minus 4 and 6 from. Okay, just multiply these two together. That's what you get. Okay, so because this is lower triangular, forward substitution. So y1 is always whatever the first element in the right-hand side vector is. So y1 is equal to 18. y2, okay, so, well, this is quite an easy one, really. y2 should just be equal to -4 because we haven't got anything there. So 1 times y2 is equal to -4. y3 is 6. Yeah, so 6 minus a third y1 minus 2/3 y2. So we've got a third of 18 is 6, so 6 minus 6, which is 0. And then we're going to have 8 over 3. Yeah, 8 over 3. So that's my y vector. Just solve using forward substitution. Once you've got that, standard is to solve ux equals y using back substitution. Okay, so the U matrix was calculated before. X are my unknowns, and my y I just calculated. Oh, sorry about the fuzziness. If I can turn autofocus off. That's better. So it's 18 minus 4, 8 over 3. Okay, so we solve that using back substitution. So starting with x3, 8 over 3, x3 equals 8 over 3. So that's x3 is just going to be equal to 1. x2 is going to be -4 plus 2 lots of 1. And x1 is going to be a third because the coefficient of x1 is 3. So that's a third. 18 minus 2 times 1 plus 2 times -2. Okay, so what we've got here, 18 minus 2 is 16, minus 4 is 12, divided by 3 is 4. And that's your solution. So the solution method using LUP is exactly the same as LU, with just the difference that we have to multiply the right-hand side vector by P. Sorry? Oh, yes. Yes, x3 is 1. So. Okay, how is that is that okay? The hardest thing there is to calculate the LUP factorization to solve the system. If you ever forget this, what order there is, just derive it. So you start with, well, what I mean by derive it, you start with AX equals B, and you know that PA equals LU. Substitute them all in, and you get the order. Or failing that, just memorize it. Okay. Right, so has everyone got this written down? Okay. So, okay, guys. Right, so we looked at using elementary matrices to calculate LUP factorization. As I mentioned last time, they're only useful for small matrices, 3 by 3s or maybe even 4 by 4s. Anything larger than that, they soon become very clunky and it takes ages. So what we tend to use is Krauts algorithm. Okay, so when MATLAB calculates LUP factorization, MATLAB will use Krauts algorithm, not elementary matrices. This is slightly more complicated than the one for LU factorization because we have to take into account row swaps. Okay, so this is the sort of general steps we take. We start with P being equal to the identity matrix. And you take, as with the Krauts algorithm we saw last time, you take each column one by one in turn, and you change the values of the matrix A. So rather than saying, okay, this is an element from L, this is an element from U, we actually change the elements in A. Okay. Depending on whether we're in the upper triangular section or the lower triangular section. So if I is less than J, in other words, the upper triangular, we calculate this one. And if I is greater than J, calculate this one. The only difference is the limit on the summation. So for each column in J, so let's say we're on the first column, we calculate Aij when J is 1. Then we look for the largest pivot in the column below Ajj. So Ajj is our pivot element. And we perform equivalent row swaps on A and P. So P, you started with the identity matrix. So any row swaps which you have on A, you also do it on P. And then you divide the elements below the pivot element by whatever it is. Okay. So you do that for each column. When you've finished, okay, you're still working with matrix A. The elements of L are just the lower triangular elements with ones on the main diagonal. The elements of U are the upper triangular elements, and your P is whatever row swaps you applied. Okay, so let's look at an example. So this is this the same matrix before? No, slightly different one. 3 by 3. Okay. Calculate Krauts algorithm for the first column. Well, for the first column, the summations are 0 because when I is less than or equal to J, okay, I would, for A11, I is 1, I minus 1, 0. So this summation doesn't exist. And for when J is 1, this summation doesn't exist. So essentially, you don't really need to bother with the first column. They're just, first column is just equal to whatever you got in the first column of A. So RA is unchanged. I left it on the slide just to be sort of complete. Then you do the pivot. So the largest pivot is in row 2, which is 6. So we do row swaps on both A and P. So swap row 1 and 2 on A and swap row 1 and 2 on P. Once you've done the row swap, we divide anything beneath the pivot by the pivot. So here's the pivot is 6. So we divide 2 and minus 4 by the pivot. We don't touch any other elements. We only do the ones beneath the pivot. So that's your first column done. Second column, okay, calculate your Aij using the formulae from before. Okay, so it's fairly similar, and that you do start to see a pattern emerging on these things. Okay, so it's all to do with A, and this is what you get if you calculate A12, A22, and A32. So we're always doing this on elements of A. Then you do the pivot swap. Okay, so the largest pivot is in row 3, because we've got 4 underneath, so we have to swap rows 2 and 3 around. Okay, so we swap rows 2 and 3 around on both A and P. And then you divide, once you've swapped, then you divide by the pivot. So the pivot is 4, so we divide 1 by 4. Third column. Okay, again, do the same thing using Krauts algorithm. you probably have to keep referring back to those formulae. You'll be given them in the exam if a question like this pops up, so don't feel the need to have to remember it. Okay, so calculate the third column. We don't do any row swaps because we're on the bottom, our pivot element's on the bottom row. So we only swap if there's an element beneath which is greater than our pivot element. So that's your final matrix A. Okay, the three lower triangular values, so in this case it's minus 2/3, 1/3, and 1/4, are our L, form our L values with the ones in the main diagonal. So you start off with your L as a identity matrix, and you just fill in the lower triangular elements with the lower triangular elements of what your A is. U is just the upper triangular element of A. P, well, that's been formed by your row swaps as you move through the algorithm. Okay, so that's Krauts algorithm, LUP. It looks at first glance more complicated than elementary matrices, but it's a lot easier when we're dealing with large matrices. So when you have to code this up, it's a lot easier. Okay, so this is the last thing we're going to look at this morning. Okay. Okay, so essentially this is the same matrix we had before, but this time we're using Krauts as opposed to elementary matrices. Okay, so we start with this. I'm not going to bother doing j equals 1 because we don't change any on the first column. So if I go down the first column and calculate the aij, okay, we don't change it. So the first thing I'm going to do is do a row swap. Okay, 0 is our pivot element, so we have to do a row swap, row 3 and row 1. Okay, so this gives us A equals 3 minus 2, 2, 102, 0, 1 minus 2. So that's our row swap. Any row swap we do to A, we must also do to P. So P starts off, remember P always starts off with the identity matrix. If we swap rows 1 and 2 around of the identity, we get that. So start off with a row swap. After you've row swapped, we divide elements beneath the pivot by whatever the pivot is. So we divide A21 and A31 by 3. And everything else is left unchanged. Okay, you only do the ones beneath. You don't. It's not a row operation. It's only in that column. So now we're on the second column, and this is when we have to go back to the formulae. Okay, so for j equals 2, I'm going to calculate for I equals 1, I equals 2, and I equals 3. Okay, so the first thing I do is calculate A12. Okay, to do that, I'm just going to switch across to the Krauts algorithm. Okay, so I12, I is less than or equal to j. So I'm going to use the top one. So I12 will be just, sorry, A12 will just be A12 minus A11 times A12. Oh, sorry, it will just be Aij, won't it? It'll just be the top one. Sorry, my fault. It's for A22 that we have that. So A22 is A22 minus A21 times A12. Okay, you start to sort of recognize that the middle, this number here is the same as the first number there. Okay, this is, by the way, these A's refer to the most recent A matrix. Okay, so we started off with a different one, now we've got this one. So A22 is 0 minus A21, which is a third, times A12, which is minus 2. And A32 is A32 minus A31 times A12. Okay, so A32, A32 is 1 minus A31, which is 0, times A12, which is minus 2. Okay, so notice we're taking that A12 there. Okay, so what I'm going to do now is I'm going to fill out the second row. So the first row, second column. The first column's unchanged. So 3, 1/3, and 0. Now I've got minus 2, 2/3, and 1. And the third row, get my hands out of the way, is unchanged. Okay, so this is calculating the Krauts step. Now we have to look to see whether there's a row swap. So at the moment, our pivot element is 2/3. Okay, the element beneath it is 1, which is larger than 2/3, so we need a row swap. So what I'm going to do is I'm going to swap row 2 and row 3 around. Okay, so if I do that, top row's unchanged, second row becomes the third row becomes the second row, and the second row becomes the third row. But if I do a row swap on A, I also must do it to P. So P, I'm just going to scroll down a bit. P is this at the moment, so I need to do swap 2 and 3 around on P. Okay, all we have to do now is the last column. So J equals 3. So A13 is just A13, which is 2. A23 is equal to A23 minus A21, A13. So A23 is minus 2. Minus A21 is 0, so it doesn't really matter what A13 is, but I'll put it anyway, so that's 2. And A33 is A33 minus A31 times A13 minus A32 times A23. Okay. Okay, so A33 is 2. A31 is, where are we? 31 is a third. A13 is 2. So that's from there, by the way. So the A13 comes from there. Minus A32 is 2/3 multiplied by A23, which is minus 2. And that's 8/3. We don't do any row swaps or dividing by pivot after that because we're at the bottom, we're at the far right hand side. Okay, so if we build our matrix together, I'm running out of space a bit here, but okay, the first column of A is unchanged, second column of A is unchanged, and the third column we just calculated. So it's 2 minus 2, 8/3. Okay, so at the end, once we've done it, we got A, and we just extract L and U from A. So L, we start off with ones on the main diagonal, zeros in the upper triangular section. And our lower triangular elements of A are just the lower triangular elements of L. U is just the upper triangular elements of A. So you know those three are going to be zeros, and you just fill out from A and A over 3. Your P, well, P is just whatever the last P was, so that was this one here. And you may recognize that from when we did it using elementary matrices before. So you do start to recognize a pattern here, like for example this one, A33, 3113, 3223. Or you can just look at the formulae from Krauts algorithm. Okay, that's a little bit more involved. With all of these methods, I suggest practicing them. They're quite easy. It's quite easy to generate, let's say, a 3x3 or 4x4 random matrix, and then just go through the steps. Check your solutions either by matrix multiplication or MATLAB LU function, and you could do that. Okay. I appreciate that was quite a lot of writing down for you guys. Any questions about this? Okay, none? Okay, come and find me in the tutorial if there's any questions. This afternoon we're doing a new chapter. We're going to do a chapter in 1 hour. Oh, sorry. Sorry? Krauts, you mean? Don't know. I don't know. I'd have to look that up. Okay, guys, I'll see you in a couple of hours.